Okay. So we have a test on Tuesday, right? Yes. I thought so. I would have checked. Okay, so Tuesday, the 19th. And the exam is just going to be problems, so it won't be short answer questions like the quiz. You don't have to like specifically study the notes for it. It'll be problems like the practice problems. Yeah, I'm not going to go into any new material. I'm just going to do problems today, but it's going to do everything up through 1D kinematics. So the unit conversion problems and 1D kinematics. Yep. Question? It just depends what kind of problems I do. Like if I do a lot of units problems, then we can fit a lot in the time. If they're 1D kinematics problems, it won't be as many. But I always try to write the test to like I try to write a test where half the people in the class will have handed it in and left and are already crying in the parking lot by the time. No, not really. But like an hour is what I try to. Half the class will be gone in an hour. That's how I think of it. So no matter how many questions it is, I don't think you'll find that it's like a race. You know. Yes. Yes. I'll give you all the conversion factors you need, and I'll give you all the equations you need. Yes. No, it'll be doing problems the same as the homework problems. And be sure that you show steps. I sometimes, like on the first exam, people hand in a test that just has answers on it. And for one thing, you know, if you get the answer wrong, you just get a 0 on the question, you know. But for another thing, I mean, what I want to see is the way you do it. I don't just want to see the answer. Because we're just trying to sort of develop approaches here, you know. But yeah, please be sure you show your steps. I want to be able to follow what you did, and if you show your steps and you think about it the right way, and you make a dumb little, you know, math mistake or whatever, you can get full credit on a problem and have the wrong answer. So that's another reason to do it. Yes. Yes, you do need to carry the units. Yeah, thanks. So this is the last test where you'll have to do that, but for the first test, you have to carry the units. The only exception is in problems where you have to use the quadratic formula. At that point, it's fine with me if you. We'll do some problems like that today, or at least one. But you don't have to carry it through the quadratic formula with the square root and stuff, but otherwise, yes. Yes? If you don't have to remember that either, I'll give you the list of any of those you need. You know, like it'll say mega is equal to 10 to the 6th and that kind of thing. But yeah, you should be ready to do problems like that. Any other questions about the test? And then we have a quiz at the end of class today. Yes. Yeah, I do put pictures on it to try to show what the problem looks like. You know, if, oh, well, you have to draw pictures. I don't think they're, you'll have to draw probably position versus time graphs like you did in the homework problems, but that's all. Yep. Yes. Yep. All those equations will be on there. So I really don't think there's, and even if there's ever an equation that I gave in class that you would like that doesn't happen to be on the test, you know, I'd be happy to write it on the board. I don't want you to feel like you have to memorize these equations. Just know how to do it, you know. Any other questions? Okay. Well, let's just do some more practice problems, and we'll just do that until it's time for the quiz. Maybe if this gets tiresome, we can, after I do a couple, we can switch to you guys working on problems together. Yes? Yeah. Like right before it hits the ground or something, before some. Oh, yeah. Sure. And it's an average velocity that we're calculating? Okay. Yeah, sure. What? Okay, we'll do one and we'll calculate an average velocity and a displacement. Yes. Oh, we did? That won't be on the test. No average speed. We change those questions in a while, and the class has changed more than the questions have. You know how to calculate instantaneous speed if you have the instantaneous velocity? Even if you're not in calculus, all you do is take off the sign. So the instantaneous velocity and instantaneous speed are the same. Speed just is always positive. And on the other hand, if you're given like an instantaneous speed in a problem and you need to turn it into a velocity, you just have to decide whether it's moving in the positive or negative direction and give it that sign. Okay, so let's just say a yo-yo starts up here and then goes down here and then comes back up. So we're just going to do like a simple thing with, so I'll call this instant 1. This is instant 2. Yo-yo takes 1 second to fall 0.25 meters, and then 2 seconds to return, to the hands. And so let's say the 0 position is at the bottom. that bottom position. And let's say the positive direction is down. So we'll draw a position versus time. Oh, and I didn't give a 0 time. So let's just say time equals 0 when it starts at the start of the motion. For the path of the thing, it's starting at the top, and it starts at the top and it drops 0.25 meters, and then it rises again 0.25 meters. So we'll do a position versus time graph, and we'll calculate the displacement from instant 2 at the bottom to instant 3 when it's back at the top. It gets back to the top at instant 3. And then we'll also calculate the average velocity. So the first thing I'm going to do before I have to consider either of the zeros or the positive direction is I'm just going to draw a number line sort of thing. I mean, it won't put numbers on it yet because we're not dealing with numbers yet. I'm just going to draw something where I can diagram what the motion looks like. And that motion doesn't have anything to do with our choices of numbers. It's just what happens. Yes? I mean, if you can make it work without that, that's fine with me, yeah. I'm just trying to give a method for anybody who's having some trouble with this. I think this way of doing it will help. Okay, so I'm going to call this point over here the top, that's the hand. And over here, I'm going to call the bottom of the motion. And the distance between these two is 0.25 meters. And the motion of the yo-yo that doesn't have anything to do with choices of numbers, it starts on the left at the top, continues the bottom, and then back to the top. So over here at the left, this is instant 1. At the right is instant 2, and then on top, on the left, is instant 3. And we also know the elapsed time between these. To go from instant 1 to instant 2 is 1 second. And to go from instant 2 to instant 3 is 2 more seconds. And so I've drawn this diagram. It has some numbers on it. It has a distance and it has 2 elapsed times. But none of that stuff is negotiable, Like, you can't say, like, no, I chose a different 0 position. That stuff doesn't change. That's the stuff that happens, and it's independent of you. But now we're going to make the choices of the 0 position and 0 time and positive direction that allows us to label these instants with times and with positions. So the problem said we're going to choose the bottom to be the 0 position. So that's the easiest position to label. This is 0. And the positive direction is down. That means it's to the right, the way that I drew that motion. It's not from the bottom towards the top, it's from the bottom away from the top. So the positive direction is this way. And now that we have both of those, we can give a position label to the top of the motion. If we start at 0 and go 0.25 meters in the negative direction, what's the position? That was so quiet. Yeah, negative 0.25. So the position label for the top is negative 0.25. And now we have to do the time labels. The 0 time was when the yo-yo is released from the hand. And so this is, 0 seconds, instant 1. And so 1 second after 0 seconds, what's the time label for instant 2? Yep, that's 1 second. And then 2 seconds after the instant 1 second, what's the label? 3 seconds. And so now what you can think of is, the way you can think of this is we have 3 instants, and each of those instants is described by a coordinate pair, where the coordinate has a time and a position. Okay, so at instant 1 here, the time is 0, the position is negative 0.25. So the coordinates on a position versus time graph are 0, negative 0.25. And at instant 2, the time is 1 second, the position is 0, so the coordinates are 1, 0. And then at instant 3, the time is 3, the position is back to negative 0.25, so the coordinates are 3, negative 0.25. So that's how I'm going to write it. So we have instant 1, instant 2, and instant 3. And the coordinates are always going to be time, position, because we have our time on the x-axis and our position on the y-axis. So instant 1 is at 0, negative 0.25. Instant 2 is at 1, 0. And instant 3 is at 3, negative 0.25. And now I'm just plotting those points on a graph and then drawing a line between them. Does anybody have any questions about this idea of like the coordinates, how I came up with those pairs? I think I haven't described them as coordinates before, but that's really what we're doing, is coming up with coordinates that we can graph then. Okay, so the y-axis is position, the x-axis is time. The times that show up in our coordinates are 0, 1, and 3. So 0, 1, 3. And the positions that show up are 0 and negative 0.25. And now, question? Now I'm just going to plot these 3 points. So the first one is 0 horizontally, negative 0.25. So that's here. The second one is positive 1 horizontally, 0 vertically, so that. And then the third one is 3, positive 3 horizontally, negative 0.25, so there. and then just connect those. Okay, so for part B, we're going to find the displacement from instant 2 to instant 3. Remember, the displacement is the position at the later instant minus the position at the earlier instant. So the position at time 3, what's the position at instant 3? Negative 0.25, and the units are meters. And then we're going to subtract the position at instant 2. What's the position at instant 2? 0. So the displacement is negative 0.25 meters. That's to get the average velocity, yep. So now we're going to do the same thing with the average velocity. So V average is P later minus P earlier divided by T later minus T earlier. And another way to think of that is the displacement divided by the time that's gone by, the elapsed time. So the displacement is negative 0.25 meters. The elapsed time between instant 2 and instant 3, what's that? Well, we can subtract it. It's the time at instant 3 is 3. The time at instant 2 is 1. Seconds. And so you get negative 0.125 meters divided by seconds. Any questions about any of those? Okay. Yes?
I would think that at the average velocity,
yeah, so you always have to specify 2 instants. And whenever someone talks about an average speed or an average velocity and they don't specify 2 instants, it's because there's 2 instants that just happen to be implied. Like if you say like, oh, my average speed for the trip was this, you're implying that your instant is the start and the end of the trip. But yeah, sort of, I think you should think of it as like there need to be 2 instants specified for it to be defined. Okay, let's do a quadratic formula problem. Okay, so let's say let's say a ball is rolling up a ramp. And it has Okay, so let's say it has an acceleration. Okay, so at the point A, its speed is 4 meters per second. Speed. So we'll have to think about directions and stuff. And it's slowing down with an acceleration magnitude of 2 meters per second squared. How long will it take for the ball to travel 1 meter? I think this is going to be a quadratic formula. That's what I was trying to think of. Okay. So the second point is 1 meter up the ramp. This is a constant acceleration problem. So the first thing we have to do is make those 4 choices. Time equals 0, time final, position equals 0, and the positive direction. So what instant do you want to correspond to time equals 0? Yeah, when it passes A, that has to be time equals 0 because we know a lot of stuff, and if we don't choose that, we'll throw that information away. You know, so time equals 0 is going to be when the ball passes A. And then what do you want to call time final? Yeah, when it passes B. And now there's more flexibility. The other two, you can get this problem right with different choices of those. But what you want to choose is a 0 position. Yeah, so if there's nothing else jumping out at you, you might as well always choose the position of the object when time is 0. So the ball's position at time equals 0. If you make that choice, that's equivalent, means exactly the same thing as saying the initial position is 0. It's just like a word game figuring out those are the same thing, you know? Because this is saying 0 is the ball's position at time equals 0, and this is saying the ball's position at time equals 0 is 0, you know? Means the same thing. And then positive direction, up or down the ramp. Up. And now we can list out what we know, want. Do we know time final? Do we want it? Yes. Do we know position initial? Yep. P sub I is 0. Do we know P final? What's that? Yeah, and you have to be careful that it is positive 1 meter in this case, but you just have to be careful with that. A is your 0. Positive is this way. So if you go start at the 0 and go 1 meter in the positive direction, you get to positive 1. So P final is positive 1 meter. And then do we know the initial velocity?
Yeah.
Okay, so we know that the speed is 4 meters per second. So now we have to think about the direction. When the ball passes A, is it moving in the positive or negative direction? Yeah, it's moving in the positive direction, so that has to be positive 4 meters per second. Do we know the final velocity? No, but we don't care. Do we know the acceleration? Okay, so we know that the magnitude of the acceleration is something, 2 meters per second squared, and now we have to think about the direction of that. So what's the thought process for the direction of the acceleration? That's exactly right. So, the velocity is positive. We know it's slowing down. So the acceleration has to be opposite the velocity. So the acceleration is negative. So acceleration is negative 2 meters per second squared. And the equation that works with these says P final is equal to P initial plus V initial times time final plus 1/2 A time final squared. So 1 meter is equal to 0 plus 4 meters per second times time final plus 1/2 times negative 2 meters per second squared times time final squared. And I'm going to get everything over on the right side. So 0 is equal to negative 1 meter plus 4 meters per second times time final minus 1/2 times 2 is 1 meter per second squared times time final squared. We have to use the quadratic formula to solve this. Well, you might be able to, if you really like math and you've done a lot of algebra and stuff, you might be able to figure out a way to solve this with factoring. But I assume most of you are just looking for the easiest approach at this point. When you see this, you want to do quadratic formula. And anybody have, can anyone explain what's the key here that tells me I want to use quadratic formula? Yep. Yep, actually, it's all three of these things. That's totally the right idea. We have a t final squared, the variable we want squared. We also have a linear term of the variable we want, just tf. And we also have a constant. And if you have all three of those things, so if you have a constant and a linear variable, and the variable squared, quadratic. Sure. Yeah, sure. Yep. The good thing about the quadratic formula, this is the consolation prize, because nobody likes the quadratic formula, but the consolation prize is that I said you can forget about the units now. So So you can drop off the units. So the equation we have is 0 is equal to -1 plus 4TF minus 1 TF squared. So we're going to label these A, B, and C. Which of these coefficients is the A? Yeah. I guess, yeah. I was going to say, is it the constant or the squared? It would be -1 for either one, but A is always the coefficient on the squared. B is the coefficient on the linear term, and C is the constant. And the formula says -b, let me make that uppercase, -b plus or minus square root of b squared minus 4ac, and then everything there divided by 2a. So TF is equal to -b divided by 2 times -1. So that's -4 divided by -2. So we get +2. You see what I'm doing here? I'm just breaking it up into -b over 2a plus or minus the square root divided by 2a. B squared is 16. 4 times a times c is, so that would be +4, and we're subtracting it. We have the square root of 16 minus 4 divided by -2. So we have 2 plus or minus oh, I see. Yeah, so I did it as, so I split it up into, one half is -b over 2a, and the other half is the square root over 2a. You don't have to do it that way. If you come to my office hours and it's not too busy and you have a graphing calculator, I'll program the quadratic formula in, and then you don't even have to think about it. So square root of 12, that's the square root of 3 times the square root of 4. Square root of 4 is 2. So that's 2 times the square root of 3 divided by 2. So 2 plus or minus square root of 3. We're looking for, yeah, I'm trying to make sense out of this. Yes? Uh-huh. Yeah, so let me not skip as many steps. We have 2 plus or minus the square root of 12 over 2, over -2. And then that's equal to 2 plus or minus 2 times the square root of 3 over -2. And the 2's cancel here. And so that's 2 plus or minus the square root of the negative square root of 3, which is the same thing as 2 plus or minus the square root of 3. Yes. So I split this up into negative b over 2a plus or minus square root of b squared minus 4ac over 2a. Okay. So we have two positive answers in this. That usually is not going to be the case. So time final is, can someone tell me what that is? It's like we have basically 0.3, 0.267 seconds, and we also have 3.73 seconds. Okay. So normally when we're solving for time with a quadratic formula, we have a negative and a positive answer. These are both positive, so that's a pain. But what happens is the ball takes off this way. It passes B. It keeps going, slowing down the whole time. It finally gets to the highest point on the ramp, turns around and comes back. Okay. So, because what we said is that the acceleration is down the ramp. So it'll, the same way as if you throw a ball up into the air, it'll slow down until it gets to its highest point, and then it'll speed up when it turns around. This ball is going to go up the ramp, slowing down the whole way, reach its highest point, and then start speeding up back down the ramp. And that's why it hits that point B 2 different times. The first time it hits it is 0.267 seconds after it starts. The second time it hits it is after it's done that whole path, 3.73 seconds, and it ends up back there. So in this case, the one we want is this one. But I promise not to make you, that's more than I expect you to do. If you do a quadratic formula, there'll be a plus and a minus, and that's it. Any questions about the problem or the quadratic formula? Yep. The way we're setting these problems up with where we always have our zero time happening before our time final, if you get a negative time, that tells you something went wrong with the math. Oh yeah, so if you get one negative time and one positive time, it has to be the positive one. Yep. Any other questions? Want to do another one or just take the quiz? Okay, me too.